Chapter 10. Hoisting, conveying and storing. Allusion has been made to the stupendous buildings and works of the ancients and of the Middle Ages, the immense multitude of workers and great extent of time and labor employed in their construction, and how the awful drudgery involved in such undertakings was relieved by the invention of modern engineering devices, the cranes, the derricks, and the steam giants to operate them, so that vast loads which required large numbers of men and beasts to move, and long periods of time in which to move them, can now be lifted with ease, and carried to great heights and distances in a few minutes, by the hands of one or of a few men. But outside of the line of such undertakings, there is an immense field of labor-saving appliances, adapted for use in transportation of smaller loads from place to place, within and without buildings, and for carrying people and freight from the lower to the upper stories of tall structures. In fact, the tall buildings which we see now in almost every great city towering cloudward from the ground to the height of 15, 20 and 25 stories, would have been extravagant and useless, had not the invention of the modern elevator rendered their highest parts as easy of access as their lowest, and at the same time given to the air space above the city lot as great a commercial value in feet and inches as the stretch of earth itself. Many of the skyscrapers, so-called, are splendid monuments of the latest inventions of this century. It is by means of the modern elevator that the business of a whole town may be transacted under a single roof. In the multiplicity of modern human contrivances by which the sweat and drudgery of life are saved, and time economized for worthier objects, we are apt to overlook the painful and laborious steps by which they were reached, and to regard with impatience, or at least with indifference, the story of their evolution, and yet no correct or profound knowledge of the growth of humanity to its higher planes can be obtained without noting to what extent the minor inventions, as well as the startling ones, have aided the upward progress. For instance, consider how few and comparatively awkward were the mechanical means before this century. The innumerable army of men when men were slaves, and when blood and muscle and brain were cheap, who, laboring with the beast, toiled upward for years on inclined ways to lay the stones of the stupendous pyramids, still had their counterparts centuries later in the stream of men carrying on their shoulders the loads of grain and other freight, and burdens from the shore to the holds of vessels, from vessels to the shore, from the ground to high buildings, and from one part of great warehouses to another. Now look at a vessel moved to a wharf, capable of holding 50,000 or 100,000 bushels of grain, and having that amount poured into it in 3 hours from the spouts of an elevator, to which the grain has been carried in a myriad buckets on a chain by steam power in about the same time, or to those arrangements of carriers, traveling on ropes, cords, wires, or cables, by which materials are quickly conveyed from one part of some structure or place to another, as hay and grain in barns or mows, ores from mines to cars, merchandise of all kinds, from one part of a great store to another, or shot through pipes underground from one section of a city or town to their destination by a current of air. True, as it has before been stated, the ancients and later generations had the wedge, the pulley, the inclined plane, the screw and the windlass, and by these powers, modified in form and increased in size as the occasion demanded, in the form of cranes, derricks, and operated by animal power, materials were lifted and transported, but down to the time of the practical and successful application of steam by Watt, in the latter part of the 18th century, and until a much later period in most places in the world, these simple means actuated alone by men or animals, were the best means employed for elevating and conveying loads, and even they were employed to a comparatively limited extent. The century was well started before it was common to employ cups on elevator bands in mills, invented by Oliver Evans in 1780, to carry grain to the top of the mill, from whence it was to fall by gravity to the grinding and flouring apparatus below. It was not until 1795 that that powerful modern apparatus, the hydraulic or hydrostatic press, was patented by Bramah in England. The model he then made is now in the Museum of the Commissioner of Patents, London. In this a reservoir for water is provided, on which is placed a pump having a piston rod worked by a hand lever. The water is conveyed from the reservoir to a cylinder by a pipe, and this cylinder is provided with a piston carrying at its top a table, which rises between guides. The load to be carried is placed on this table, and as the machine was at first designed to compress materials, the load is pressed by the rising table against an upper stationary plate. The elevation of the table is proportionate to the quantity of water injected, and the power proportionate to the receptive areas of the pump and the cylinder. The first great application of machines built on this principle was by Robert Stephenson in the elevation of the gigantic tubes for the tubular bridge across the Menai Straits, already described in the chapter on civil engineering. The century was half through with before it was proposed to use water and steam for passenger elevators. In 1852, J.T. Slate in England patented a device consisting of a drum to be actuated by steam, water, or compressed air, around which drum ropes were wound, and to which ropes were attached separate cages in separate wells to counterbalance each other, the cages moving in guides, and provided with brakes and levers to stop and control the cages in the movement of the drum. Louis T. Van Elvian, also of England, in 1858 invented counterbalance weights for such lifts. Otis, an American, invented and patented in America and England in 1859 the first approach to the modern passenger elevator for hotels, warehouses, and other structures. The motive power was preferably a steam engine, and the elevating means was a large screw placed vertically and made to revolve by suitable gearing, and a cylinder to which the car was attached, having projections to work in the threads of the screw. Means were provided to start and to stop the car, and to retard its otherwise sudden fall and stop page. Elevators, which are now so largely used to raise passengers and freight from the lower to the upper stories of high edifices, have for their motive power steam, water, compressed air, and electricity. With steam a drum is rotated over which a hoisting wire rope is wound, to which the elevator car is attached. The car for passengers may be a small but elegantly furnished room, which is carried on guide blocks, and the stationary guides are provided with ratchet teeth, with which pawls on the car are adapted to engage, should the hoisting rope give way. To the hoisting rope is attached a counterbalance weight to partly meet the weight of the car, in order to prevent the car from sticking fast on its passage, and also to prevent a sudden dropping of the car, should the rope become slack. A hand rope for the operator is provided, which at its lower end is connected with a starting lever controlling the valves of the cylinders, into which steam is admitted to start the piston shaft, which in turn actuates the gear wheels, by which movement the ropes are wound around the drums. In another form of steam elevator, the drums are turned in opposite directions by right and left worms driven by a belt. In the hydraulic form of elevator, a motor worked by water is employed to lift the car, although steam power is also employed to raise the water. The car is connected to wire cables passing over large sheaths at the top of the well room to a counterbalancing bucket. This bucket fits closely in a watertight upright tube, or standpipe, about 2 feet in diameter, extending from the basement to the upper story. Near this standpipe in the upper story is placed a water supply tank. A pipe discharges the water from the tank into the bucket, which moves up and down in the standpipe. There is a valve in the tank which is opened by stepping on a treadle in the car, and this action admits to the bucket just enough weight of water to overbalance the load on the car. As soon as the bucket is heavier than the car it descends, and of course draws the car upward, thus using the minimum power required to raise each load, rather than, when steam is employed, the full power of the engine each and every time. The speed is controlled by means of brakes or clamps that firmly clasp wrought iron slides secured to posts on each side of the well room, the operator having control of these brakes by a lever on the car. When the car has ascended as far as desired, the operator steps upon another treadle in the car connected with a valve in the bottom of the bucket, and thus discharges the water into the receiving tank below until the car is heavier than the bucket, when it then of course descends. The water is thus taken from the upper tank into the bucket, discharged through the standpipe into the receiving tank under the floor of the basement, and then pumped back again to the upper tank, so that it is used over and over again without loss. Various modifications have been made in the hydraulic forms. In place of steam, electricity was introduced to control the hydraulic operation. Again, an electric motor has been invented to be placed on the car itself, with connected gearing engaging rack bars in the well. Elevators have been contrived automatically controlled by switch mechanisms on the landings, and in connection with the electric motor safety devices are used to break the motor circuit and thus stop the car the moment the elevator door is opened. And there are devices to break the circuit and stop the car at once, should an obstruction, the foot for instance, be accidentally thrust out into the path of the car frame. Columns of water and of air have been so arranged that should the car fall, the fall will be broken by the water or air cushion, made to yield gradually to the pressure. So many safety devices have been invented that there is now no excuse for accidents. They result by a criminal neglect of builders or engineers to provide themselves with such devices, or by a most ignorant or careless management and operation of simple actuating mechanisms. Between 1880 and 1890 there was great activity in the invention of what is known as store service conveyors. One of the earliest forms, and one which had been partly selected from other arts, was to suspend from a rigid framework connected to the floor, roof, or side of the building, a long platform in the direction through the building it was desired the road to run, giving this platform a slight inclination. On this platform were placed racks, and from the tracks were suspended trucks, baskets, or other merchandise receptacles, having wheels resting on and adapted to roll on the tracks. Double or single tracks could be provided as desired. The cars ran on these tracks by gravity, and considerable ingenuity was displayed in the feature alone of providing the outgoing and returning inclined tracks, in hand straps and levers for raising and lowering the carriage, part or all of it, to or from the tracks, and in buffers to break the force of the blow of the carriages when arriving at their stopping places. Then about 1882-83 it was found by some inventors if moderately fine wires were stretched level and as tight as possible, they would afford such little friction and resistance to light and nicely balanced wheels that no inclination of the tracks was necessary, and that the carriages mounted on such wheels and tracks would run the entire length of a long building and turn corners not too sharp by a single initial push of the hand. In other arrangements a carrier is self-propelled by means of a coiled spring on the carrier, which begins its operation as soon as the carrier is given a start, and to meet the exhausted strength of such spring, coiled springs at different points on the line are arranged to engage and give the carrier an additional push. Before the carrier is stopped its action is such as to automatically rewind its spring. A system of pneumatic transmission was invented, by which a carrier is caused to travel through a tube by the agency of an air current, created therein by an air compressor, blower, or similar device. The device is so arranged that the air current is caused to take either direction through the tube, and in some instances, gravity may be used to assist a vacuum formed behind a carrier. The tube is controlled at each end by one or more sliding gates or valves, and the carrier is made to actuate the gates and close the one behind it, so that the carrier may be discharged without permitting the escape of the air and consequent reduction of pressure. An interesting invention has been made by James M. Dodge of Philadelphia in the line of conveyors, whereby peat coal and other quite heavy materials introduced by a hopper into a trough are subjected to a powerful air blast which pushes the material forward, and as the trough is provided with a series of frequently occurring slots or perforations open to the outer air and inclined opposite the direction of travel, the powerful current from the blower in escaping through such outlets tends to lift or buoy the material and carry it forward in the air current, thereby greatly reducing frictional contact and increasing the impelling operation. The inventor claims that with such an apparatus, many tons of material per hour may be conveyed with a comparatively small working air pressure. In order that a conveyor carriage may be automatically switched off at a certain place or station on the line, one mode adopted was to arrange at a gate or station a sort of pin or projection or other deflector to engage some recess or corresponding feature on the carriage, so as to arrest and turn the carriage in its new direction at that point. Another mode was the adoption of electromagnets, which would operate at a certain place to arrest or divert the carriage, and in either case, the carriage was so constructed that its engaging features would operate automatically only in conjunction with certain features at a particular place on the line. Signals have been also adopted, in some cases operated by an electric current, by which the operator can determine whether or not the controlling devices have operated to stop the carrier at the desired place. By electric or mechanical means it is also provided that one or more loop branches may be connected with or disconnected from the main circuit. The lazy tongues principle has been introduced, by which a long lazy tongues is shot forth through a tube or box to carry forward the carriage, and the same principle is employed in fire escapes to throw up a cage to a great height to a window or other point, which cage is lowered gently and safely by the same means to the ground. Buffers of all kinds have been devised to effect the stoppage of the carrier without injury thereto, under the different degrees of force with which it is moved upon its way, to prevent rebounding, and to enable the carrier to be discharged with facility at the end of its route. Among the early mechanical means of transporting the carriage was an endless cable moved continuously by an engine, and this adoption of cable principle in store service was coeval with its adoption for running street cars. Also, the system of switching the cars from the main line to a branch, and in different parts of the city, at the same time that all lines are receiving their motive power from the main line, corresponds to the manner of conveying cash to all parts of a building at the same time from many points. To the great department store or monstrous building wherein, as we have said, the whole business of a town may be transacted, the assemblage and conjoint use of elevators and conveyors seem to be actually necessary. A very useful and important line of inventions consists in means for forming connections between rotary shafts and their pulleys and mechanisms to be operated thereby, by which such mechanism can be started or stopped at once, or their motion reversed or retarded, or by which an actuating shaft may be automatically stopped. These means are known as clutches. They are designed often to afford a yielding connection between the shaft in a machine, which shall prevent excessive strain and wear upon starting of the shaft. They are also often provided with a spring connection, which, in the rotation of the shaft in either direction, will operate to relieve the strain upon the shaft or shafts and its driving motor. Safety clutches are numerous, by which the machine is quickly and automatically stopped by the action of electromagnets, should a workman or other obstruction be caught in the machinery. Electric auxiliary mechanism has also been devised to start or stop the main machine slowly, and thus prevent injury to smaller delicate parts of complicated machines, like printing presses for instance. Clutches are arranged sometimes in the form of weights, resembling the action of the weights in steam governors, whereby centrifugal action is relied upon for swinging the weights outward to effect a clutching and coupling of the shaft or other mechanism, so that two lines of shafting are coupled, or the machine started or speeded at a certain time during the operation. In order to avoid the great mischief arising sometimes from undue strain upon and the breaking of a shaft, a weak coupling composed of a link is sometimes employed between the shaft and the driven machine, whereby, should the force become suddenly too great, the link of weaker metal is broken, and the connection between the shaft thereby destroyed and the machine stopped. To this class of inventions, as well as to many others, the phrase labor-saving is applied as a descriptive term, and as it is a correct one in most instances, since they save the labor of many human hands, they are regarded by many as detrimental to a great extent, as they result in throwing out of employment a large number of persons. This derangement does sometimes occur, but the curtailment of the number of laborers is but temporary after all. The increased production of materials, resulting from cheaper and better processes, and from the reduced cost of handling them, necessitates the employment of a larger number of persons to take care of, in many ways, the greater output caused by the increased demand. The new machinery demands the labor of additional numbers in its manufacture. The increase in the size and heights of buildings involves new modes of construction, and a greater number of artisans in their erection. New forms of industry springing from every practical invention which produces a new product or results in a new mode of operation, complicates the systems of labor, and creates a demand for a large number of employers and employees in new fields. Hence, it is only necessary to resort to comparative statistics, too extensive to cite here, to show that the number of unemployed people in proportion to the populations is less in the present age than in any previous one. In this sense, therefore, inventions should be classed as labor-increasing devices.